Thanks for the introduction. I'm Aarushi, and I'm going to talk about our work on adding verifiability to homomorphic secret sharing. This is joint work with Arka Rai Chaudhary, Aditya Hegde, and Abhishek Jain. Okay, so let's first start by recalling the notion of homomorphic secret sharing, or HSS, that was introduced by Boyle, Gilboa, and Ishai in 2016. So an HSS scheme enables a client to split his secret input into multiple shares and distribute them amongst a group of servers who can then homomorphically compute on these shares to evaluate some function f. And this function f is evaluated using an evaluation algorithm that maps these input shares to their corresponding output shares. And as depicted here, the servers do not communicate with each other during this evaluation process. And once the evaluation phase is over, the final output can be reconstructed by simply adding the output shares computed by the individual servers. A typical HSS scheme should satisfy correctness, which simply means that the sum of all these output shares is the correct computation of function f on the initial secret share input. It should also satisfy security or privacy, which simply means that the individual shares that are dealt to the servers hide the secret input x. And finally, HSS schemes also satisfy succinctness, which means that both the input shares and the final output shares are succinct and independent of the size of the function that was evaluated using the HSS scheme. It's easy to see that such homomorphic secret sharing schemes enable private delegation of computation. In fact, non-interactive private delegation of computation, which in turn have several applications to sublinear MPC, multi-server PIR, pseudo-random generation of correlations, etc. As a result, HSS has been a very well-studied area of research, and now we have several known constructions of HSS based on a variety of assumptions. However, all of these homomorphic secret sharing schemes, except for one that's highlighted here, which I will talk about later, focus only on the semi-honest setting. And what that means is that these constructions assume that the servers are semi-honest and hence will compute the evaluation algorithms honestly. As a result, the reconstructed value is always guaranteed to be correct. Given the state of the art, in this work, we shift our focus to malicious servers. In particular, we assume that some or all of the servers involved in these evaluations could potentially be malicious. And hence, they can deviate from the prescribed honest evaluation strategy. And in this setting, we ask if it's possible to somehow still verify correctness of the output. Viewed from the perspective of private delegation of computation, what we seek here is a private and verifiable delegation of computation. Motivated by this application, we want the final output to be verifiable not just by the client, but by any external auditor who may not have knowledge of the initial secret shared input. Also, I should note that while there are some folklore candidate solutions for this problem, in this work, we are going to focus only on a black box solution. That is a solution that only makes black box use of cryptography. Okay, so to address this problem, we introduce a new notion, which we call HSS with verifiable evaluation. HSS with verifiable evaluation preserves all of the nice features of a regular homomorphic secret sharing scheme, and in addition to that, it adds verifiability to the reconstructed output. So similar to a regular HSS scheme, HSS with verifiable evaluation has a sharing algorithm, an evaluation algorithm, and then a reconstruction phase. Well, as we just discussed, since we assume that the people evaluating on these shares could potentially be malicious, we assume that this output Y that's computed during reconstruction is only a candidate output. So in addition to all of these algorithms, we also have a verification algorithm that helps us verify correctness or validity of this candidate output. Okay, so similar to HSS, HSS with verifiable evaluation also needs to satisfy correctness, which in the setting means that if everybody behaved honestly, then the verification algorithm outputs accept, and the candidate output is indeed equal to the correct evaluation of the function f on the original secret shared input. Again, we also need succinctness in this notion, which here, in addition to requiring succinctness of input and output shares, requires that the verification algorithm should also be succinct in that it should run in time smaller than the size of the function that was evaluated. And finally, for privacy, we augment the privacy notion from a regular HSS scheme. And in this setting, we say that privacy should hold even if the malicious servers are able to see the outcome of the verification algorithm. So even if they're able to tell whether or not their potentially malformed output was accepted or not, they can privacy of the original input still holds. So these properties were analogous to a regular secret sharing scheme, but in HSS with verifiable evaluation, we also additionally require two soundness properties. And in particular, we want these soundness guarantees to hold even when all servers are malicious. I want to emphasize that this is different from privacy, where we only required privacy in case at most a subset of the servers were corrupt or malicious. For soundness, we want soundness to hold even when everybody is corrupt. So the first soundness notion that we require is local soundness, which is essentially a way to ensure the client that their secret shared input was indeed used in the evaluation of this particular function. So in other words, we say that an HSS with verifiable evaluation satisfies local soundness if verify outputs accept, if and only if Y is the correct evaluation of F on input X. And as I had mentioned earlier, our main motivation behind this notion is private and verifiable delegation of computation, which is why we also want the final proof to be publicly verifiable and not just verifiable by the client. And hence, we require a public soundness notion, which essentially means which essentially allows anybody who doesn't have access to the original input to still be able to verify correctness of the output. And so what this notion formally means is the following. Let's assume that the input can be divided into two components, a public component and a private component, where the public component is known to everybody, including the servers and, let's say, a potentially external auditor, but the private component is only private to the client. In this case, we say that a scheme satisfies public soundness if verify outputs accepts, if and only if there exists some private component of X such that Y is the correct evaluation of F on that private component plus the public component. Okay, so given this notion, let me now quickly sort of talk about some existing works that are somewhat related to verifiability and homomorphic secret sharing. So the first one is by Abram et al. This is the exception that I had pointed out in one of the earlier slides. This recent work designs a maliciously secure sublinear MPC that's based on HSS. The difference between their setting and our setting is that they only require output to be correct if at most a subset of the parties are corrupt. In contrast, like I just mentioned on the previous slide, we want soundness or correctness to hold even when potentially all of the servers are corrupt. And there are also a bunch of these other papers that I've listed here that define varying notions of verifiability in homomorphic secret sharing, but most of them do not consider the kind of soundness notion that we require. And a couple of ones that were recently broken by some of the by some results, and also those schemes only focused on very, very simple classes of functions. Okay, so now the question is, can we actually design a homomorphic secret sharing scheme with verifiable evaluation that only makes black box use of cryptography? And I'm happy to report that we indeed can. We design a general framework for transforming semi-honest homomorphic secret sharing to HSS with verifiable evaluation using some special types of ZK snarks, which I'll talk about later in my slide. And I should clarify here that by semi-honest HSS, I'm only talking about HSS schemes that have at most negligible error incorrectness. Our framework currently cannot support HSS schemes that have non-negligible correctness error. Also, I just want to clarify one more thing, that so far in all of these definitions and diagrams, I've only been talking about or showing two servers. This is just because all known HSS schemes that fit into our framework only support two parties, but our framework is general, and if in the future we were to come up with an HSS scheme that fits into this definition, our framework will work with that. Okay, so in addition to our general framework, we then show that this construction or this framework has applications to a black box solution for private and verifiable delegation of non-cryptographic and some cryptographic computations, which I'll mention towards the end of my talk. And finally, this I won't have time to talk about, but we also have extensions to the multi-client setting. So far, I've only talked about the setting where there's a single client, but we do also have results in the multi-client setting, but I don't think I'll have time to talk about that. Okay, so let's talk about instantiating this particular framework to see what kind of results we obtain. So in the paper, we present two instantiations. In our first instantiation, we can start with any of these HSS schemes and instantiate our compiler using the Groth16 snark, which is proven secure in the generic group model. And combining these two, we get HSS with verifiable evaluation for the following function classes. And in our second instantiation, we again start with the same set of semi-honest HSS schemes and instantiate our compiler with a new zero-knowledge variant of the Waters-Wu-Barg scheme that's based on subgroup decision assumption and obtain HSS with verifiable evaluation for the following function classes. Here, SIMD NC1 and SIMD P/poly just means a batched version of NC1. So it's just a group of NC1 circuits stacked parallelly. Okay, so that was a quick summary of our main results. Let me now get into the technical details. So we know that in general, zero-knowledge proofs are the most common way of adding verifiability to any kind of computation. And so this is also what we are going to use. But before talking about our construction, let me quickly review a GMW-inspired strawman approach for adding verifiability to homomorphic secret sharing. Okay, so the celebrated result by Goldreich, Micali, and Wenderson showed us how to augment or upgrade any semi-honest MPC to withstand malicious corruptions. And this was done by having each of the participants attach a zero-knowledge proof along with every message they send to prove that or attest that they performed the evaluation or computation honestly. A similar approach can also be used to add verifiability to HSS schemes, where in addition to computing these output shares using the evaluation algorithms, we can ask the servers to also attach zero-knowledge proofs, certifying that they performed these evaluation algorithms honestly. And these additional proofs can later be verified during the reconstruction phase to check whether the computation or the final output is indeed correct or not. However, while this approach seems reasonable, it inevitably requires requires us to make a non-black box use of cryptography, and that's because eval function here, the evaluation algorithm of the HSS scheme, relies on cryptographic operations, and giving a proof about such cryptographic operations will require us to make non-black box use of cryptography, which we want to avoid here. Okay, so in order to avoid such non-black box use of cryptography, our initial idea is to have the servers jointly compute a single snark proof rather than attaching individual proofs proving that each of them behaved honestly. So in particular, we want the servers to compute some partial proofs or proof shares that correspond to a single proof and can be reconstructed in the reconstruction algorithm. And what this proof is doing is certifying that f of x is indeed equal to the candidate output y. Note that this is different from the kind of proofs that we discussed in the strawman approach, where the proof was trying to prove that the evaluation algorithm was computed honestly. This is just guaranteeing that the final output is the correct output with respect to the initial input and f. So this proof can, in the reconstruction phase, be verified with respect to the original input and the candidate output, yeah, so that'll be the reconstruction phase. But now the question is, how do we generate these proof shares, or how do we enable these servers to non-interactively compute proof shares of a common proof? One idea would be to use the homomorphic secret sharing scheme itself, but as before, that idea doesn't work simply because the prover algorithm is now a cryptographic function, and evaluating it inside HSS will require making non-black box use of the cryptographic operations involved in the generation of that proof. So this idea doesn't seem to work. However, I want to emphasize that since these proof shares need to be computed non-interactively and in a distributed manner, using homomorphic secret sharing in some way or the other is our only hope here. And so in the next few slides, what I'm going to do is I'm going to show how or what ideas we develop to implement this idea without being able to make without making any black box use of cryptography. Okay. So since all snark computations rely on cryptographic hardness assumptions, generating a snark proof for any kind of arithmetic computation involves two kinds of operations, namely non-cryptographic operations, which are just simple field arithmetic, and cryptographic operations. Our next idea to avoid making any non-black box use of cryptography is to only use HSS to compute the non-cryptographic operations involved in the snark generation, and later on develop some other ideas to deal with the cryptographic operations. However, the problem is that even though these are the only two types of operations involved in snark generation, these two operations could be highly intertwined, and hence it's not clear how one would come up with a way to sort of go in and out of an HSS scheme to enable this kind of distributed non-interactive generation of the proof. So to remedy this, let's now turn our attention to a special type of snarks where there is a cleaner separation between cryptographic and non-cryptographic operations, and we refer to such snarks as splittable snarks. And these snarks have the following structure. So the prover algorithm is basically split into two parts. The first part takes the witness, the statement, and the CRS as input and performs some low-depth non-cryptographic operations. By low depth here, I mean that the computational depth of the step should be such that this overall computation can be executed within a class of functions that are currently supported by existing HSS schemes. And given the output of this particular step along with the CRS, the second step then computes the required cryptographic operations. But now, since we want these operations to be computable in a distributed manner and without requiring interaction, we want this these cryptographic operations or the second step to be linearly distributable. And what that means is the following. Let's say we have some additive shares of the output of the first step of the computation, which is mu. What we now want is that for the second step, the parties can individually apply the second step on their individual shares, and the outcome of this computation is proof shares that can later be reconstructed using some simple and efficient algorithm. Okay, so given such splittable snugs, our idea to use homomorphic secret sharing to compute these snugs in a black box manner is the following. So instead of actual witness and statement, we assume that the servers have HSS shares of the witness and the statement, which they use to compute the first part of the proof using HSS. As a result of this, they obtain additive shares of mu, which is the output of this first step. Now, given these additive shares, they can locally compute the second step on these additive shares to obtain shares of the final proof or partial shares. So this is the basic idea. Now let's see how we can use this to obtain a candidate approach for homomorphic secret sharing with verifiable evaluation. So in this construction, what we want to do is augment a regular HSS scheme to include proof shares for the following deterministic relation, which is that F computed on the initial secret shared input X results in the final candidate output Y. For this, our candidate approach now is the following. So the client will start by secret sharing its input X. The servers, as before, will use HSS evaluation to compute the corresponding output shares. But now, in addition to these output shares, the servers are also going to use HSS evaluation to compute shares of the intermediate step or the first step of the snark proof. And given these shares, they can now locally compute the second step of the snark proof to compute shares of the final proof or partial proofs. And all of these computations together are going to form the new evaluation algorithm of our HSS with verifiable evaluation scheme. In the reconstruction algorithm, the client can reconstruct both the candidate output as well as the proof, and then check the validity of this output with respect to its initial input and this candidate output. Okay, so this is a candidate approach. Let's now see if it satisfies the properties that we required of a HSS scheme that has verifiable evaluation. So it's easy to see that the scheme does satisfy correctness and succinctness. It also satisfies local soundness because the proof that we are attaching or that we just talked about here is exactly the guarantee that the client wanted or that we wanted in local soundness, which is to ensure that the output that's computed is computed using the initial secret shared input. But since this proof can only be verified by a client because it needs the verification algorithm takes the initial input X or the initial secret X as input, the scheme currently or as it is does not achieve public soundness. Moreover, it's unclear if the scheme achieves privacy. And this is just because, if you recall, our notion of privacy is stronger than that in a regular secret sharing scheme. What we want for privacy in this construction is that privacy should hold even if the servers learn whether or not the client accepted the final proof and the output. So we'll talk about public soundness later. Let's first talk about privacy and see how we can ensure privacy or whether the scheme as it is already satisfies privacy. Okay, so for privacy, there are a couple of things that we need to make sure. But first, let's assume that this first part of the evaluation is done by a corrupt server, and the second part of the evaluation is done by an honest server. Now, since we allow for malicious corruptions, the shares of the candidate output Y that's computed by these parties may not be correct. And in this case, the question is it safe to reveal the candidate output Y or the share computed by the honest party before the parties are ensured that this output is correctly computed? In general, if you recall, in MPC protocols, it's not safe to reveal malformed outputs just because it may leak some additional information about the initial secret inputs. But in this setting, what we observe is that it's actually safe to reveal this output share, and that's simply because we are working in a non-interactive setting. So unlike in the interactive setting, where the output or the messages computed by an honest party could be influenced by the corrupt party, here, since the servers never actually talk to each other, the message computed by the honest server is never going to be incorrect. And so any sort of incorrect output that can potentially be reconstructed could only be because the share computed by the malicious server was malformed. Okay, so this is fine. Our next problem that we need to worry about is how do we predict the output of the honest client in the ideal world based only on the output share computed or based only on the proof share computed by the corrupt server. Recall that for privacy here, we need the simulator in the ideal world to be able to simulate a joint view of the adversary as well as the output of the honest client. The view of the adversary here is easy to simulate, but the output of the honest client depends on whether or not the proof that it reconstructs verifies or not. And that proof can only be verified using the secret input X, which the simulator doesn't have. And so in a scenario where, let's say, the malicious server computes the output honestly, but then deviates from the honest strategy for computing the proof share, we have no way to tell whether this final proof is going to verify or not. And as a result of that, we don't know what to predict about the output of the honest client in the ideal world. And so to resolve that, we introduce this new notion that we call distributed prover robust verification. And we require these splittable snags that we use in our construction to also additionally satisfy this particular property. And what this property states is the following. So for any fixed proof share computed by an honest server, we say that a snark proof satisfies distributed prover robust verification if a PPT adversary can only find one unique proof share such that the overall reconstructed proof verifies. In other words, there's only one unique proof share that the adversary could have come up with, which will lead to an accepting proof. And that is the proof share that is obtained by honestly running the evaluation algorithm that we just designed. And so now, if we have splittable snags that do satisfy this additional property, then our simulation strategy becomes simple, where the simulator can simply look at the proof share that's computed by the malicious server, also compute the proof share that it expects the malicious server to have computed, check if the two values are equal, and if they are, then we know that the client will accept the proof. If not, we know that the client will abort with very high probability. So that's all we have for privacy. Now the only property that remains is public soundness. So for public soundness, we have a simple idea. So we were already computing a local proof that was meant for the honest client to verify if the output was computed honestly using this input that they secret share. For public soundness, what we ask is that the servers compute one more proof, which we'll call public proof. And this public proof is going to be for the following relation. So as before, we're going to assume that our input has two components, a public component and a private component. And the relation that is going to be proved using the second public proof is that there exists some private part of the input X, such that F on the private part of X and public part of X is equal to the candidate output. And note that verifying a proof for this particular relation doesn't require knowledge of X, and hence can be publicly verified, and that's how we're going to ensure public soundness. One thing to note here is that for the public proof, because it's going to be publicly reconstructed, we're going to have to use a zero knowledge snark, not just a regular snark, because a regular snark might leak information about the witness. Okay, so now we have a construction that satisfies all of the properties that we needed, and it only makes a black box use of cryptography. And here is a quick summary of this construction. So we have a client who initially secret shares an input X, and then the servers subsequently use HSS eval to compute output shares for this function f that the client wants them to compute. And in addition to that, the servers compute partial proofs or proof shares for two proofs. One is a local proof, which I'm denoting with the blue whatever image here, and the green one corresponds to the public proof. And so that's it. This is our construction. Okay, but clearly this construction assumes that these splittable snarks that also additionally satisfy distributed prover robust verification exist. But do they really exist? So we show that Groth16 ZK snarks, which are one of the most commonly used zero-knowledge snarks and are proven secure in the generic group model, satisfy all of the structural requirements of splittable ZK snarks and also have distributed prover robust verification. In addition to that, we designed a new zero-knowledge BARG scheme that's based on the Waters-Wu BARG, ensure that that is also splittable and satisfies all of the and satisfies distributed prover robust verification. And importantly, unlike the Groth16 construction, this construction is proven secure in the standard model. But unlike Groth, this only works for BARGs or batch arguments. Also, I mean, we didn't prove this formally, but we believe that all linear PCP-based zero-knowledge snarks should, at the very least, satisfy the structural properties that we require from suitable snarks. It remains to see if we can also prove that these schemes satisfy distributed prover robust verification. Okay, so just to give you sort of some idea about, what these structural properties look like and why Groth16, for example, satisfies these structural requirements, let me give a quick overview of Groth16. So a Groth16 prover proceeds in 3 steps. The first is called extended witness generation, which is essentially equivalent to generating a computation trace given the statement witness as input to a relation circuit. So it's essentially equivalent to computing all of the intermediate wire values that are induced within this relation circuit when evaluated on the statement and witness. Given this extended witness, the next step is to compute perform some other just constant depth field operations. And after the second step is finally when the CRS comes into play. And this third step is where we require cryptographic operations. So this third step essentially requires the prover to perform some group exponentiations. And this is the only cryptographic component in Groth16. And the output of this third step is the final proof, which in Groth16 is just 3 group elements. Let's denote them by ABC. Okay, so I said Groth16 satisfies all the structural requirements of a splittable snark. And that's because these first 2 steps together are just low-depth non-cryptographic operations. So the generation of extended witness can be computed in the same sort of amount, in the same depth as the depth of the relation circuit. And in addition to that, we only require some constant depth field operations. And so if you're designing, let's say, an HSS scheme with verifiable evaluation for some particular functions with some depth, the first step will require computations of a similar depth, and the second step only adds some additional constant depth computations. And now, given the output of the second step, like I'd mentioned on the previous slide, the third step requires computing group exponentiations. In particular, here, these QIs denote the group elements that are generated in the CRS. And let's say these alphas are the output of the second step. So now you can see that if, for example, the servers were to use HSS to compute the first two steps to obtain additive secret sharings of these alpha I values, they can individually compute these group exponentiations given the CRS. And I mean, once all of the servers have computed their individual partial proofs or proof shares, it's easy to combine the proof shares. Which is why this third step satisfies linearly distributable cryptographic operations requirement that we have. And as a result, you can see that Groth16 snarks are indeed splittable. In our paper, we also show that these Groth16 snarks satisfy distributed prover robust verification. I'm not going to talk about that in this talk, but we'll hopefully post our paper on ePrint soon, and I invite you to take a look. Okay, so that's all I wanted to talk about in the construction. Now let's quickly talk about the applications of this particular notion. So like I'd mentioned earlier, the main motivation that we had for defining this notion was private and verifiable delegation of computation. So this particular construction that we have can be used for private and verifiable delegation of non-cryptographic computations or functions. And in particular, our solution yields the following interaction pattern, where a client can first send some information to the servers who do some computation, and whatever computation they do can then be publicly reconstructed and verified. The client does not need to come back online or intervene here. So what our solution yields is a truly non-interactive and black box approach for private and verifiable delegation of computation. In contrast, if we were to use an FHE-based approach, the interaction pattern slightly differs. So in known FHE-based solutions for verifiable and private delegation of computation, the client actually does need to come back online once the server is done computing the proof, computing the output. And as a result, you can see the client first sends some information to the server, who then has to again send back some information to the client before the information that the client wants to send out becomes publicly verifiable. Okay, so this was about delegating non-cryptographic computations, and we said that we have a black box solution for that. But what if I want to delegate some cryptographic computations? Is it still possible to delegate a cryptographic computation while being black box in the cryptographic operations that are used in that particular function? So we show that for zero-knowledge snark computations, our construction does actually yield a black box and non-interactive solution for delegating zero-knowledge snark computations. In particular, let's assume that a client wants to outsource the computation of a splittable zero-knowledge snark for this particular relation, where F is, let's say, the relation circuit, X is some statement, and what we want to check is whether there exists a witness such that F of X comma W is equal to 1. How would we do this using HSS with verifiable evaluation, and in particular our very scheme that we constructed? So what we're going to do is we can use an HSS with verifiable evaluation for computing the function F, which is the relation circuit here. And when we do that, what happens is that the servers will automatically also compute shares of a proof that proves exactly this relation that we wanted it to compute in the first place. So these proof shares actually correspond to the shares of the zero-knowledge snark that we wanted to delegate to these servers. And so here again is an example of verifiable and private delegation of computation, of cryptographic computation that you can achieve using our construction. And in comparison to some of the prior results that also focus on outsourcing zero-knowledge SNARK computations, we do have some advantages. So for instance, there are two main approaches that have been used in prior works. One is an MPC-based approach, and the other is an FHE-based approach. So the drawback of MPC-based approaches, even though they are currently more efficient in practice, is that they require several rounds of interaction. And in contrast, as we've just discussed, our construction is completely non-interactive. And in comparison to FHE-based solutions, our approach has two advantages. First, as in the case of non-cryptographic operations, the client doesn't need to intervene, and we get a fully non-interactive solution. Moreover, in known construction that's based on FHE, the final proof that the server generates is slightly different from the original zero-knowledge SNARK scheme that the client initially wanted to delegate. Whereas in our setting, as we've just seen, the final proof that's generated is in fact the exact same zero-knowledge SNARK that the client wanted the servers to generate in the first place. Okay, so I think that's all I had. Let me quickly summarize. So we introduce a new notion of HSS with verifiable evaluation. We present a general framework for adding this kind of verifiability to semi-honest HSS schemes using a notion of splittable SNARKs that we define here. We also present some instantiations of splittable SNARKs, and as applications, we show that this notion has application to verifiable delegation of non-cryptographic and zero-knowledge SNARK computations. Also, this is something that I didn't get a chance to talk about, is that we also have results in the multi-client HSS with verifiable evaluation setting, and also applications of that to delegation of computation. Okay, so I'll conclude with a couple of open questions. The first and the biggest open question is, can we sort of upgrade this framework to also be able to use semi-honest HSS schemes that have a non-negligible correctness error? As I had mentioned earlier, our framework currently necessarily requires the semi-honest HSS scheme that we start with to have at most a negligible correctness error, but it would be interesting to see if there's a way to sort of upgrade this framework. The next open question would be to sort of find other examples of splittable SNARKs. In our paper, we only show 2 examples, and we are hopeful that other linear PCP-based zero-knowledge SNARKs also satisfy these properties, but we haven't checked that yet. Also, I mean, finding other applications of zero-knowledge of these kind of splittable SNARKs that have these nice structural properties, I think could be interesting. And finally, I want to remark that this notion of distributed prover robust verification is just a way to sort of add some sort of verifiability to the individual proof shares that's computed by the servers. And one potential way, or sort of like the more traditional way to do this, is using MACs. If we could somehow enable the servers to compute a MAC on their proof shares, that would, and I mean, we can then rely on unforgeability of the MAC scheme to ensure that a malicious server cannot find more than one proof share that will lead to an accepting proof. But sort of implementing this idea requires more care and sort of carefully choosing the MAC scheme that's compatible with the HSS scheme, the HSS scheme and the zero-knowledge SNARK that you pick. But if we're able to sort of figure this way out, then we won't have to rely on this additional distributed prover robust verification property of splittable SNARKs. Just the structural requirement on these kind of SNARKs would be sufficient because we will be able to achieve a similar property just using MACs. And that's it. Yeah, thank you.